Today we will start a new topic. We will start talking about now angle modulation. Right now, let me start with a brief general discussion. So far we have been talking about amplitude modulation, right? And briefly, how do you describe amplitude modulation? Some way of embedding the variations of the message signal on the amplitude of the carrier signal, right? So basically the amplitude of the carrier signal is modified in accordance with the amplitude of the message signal. So the information content lies in the amplitude of the carrier, right? Now there are other ways of embedding information into a carrier. Amplitude is not the only way. You want some parameter, in general you want some parameter of the message, the amplitude of the message signal to modify some parameter of the carrier, right? What are the other possible parameters you can modify? You can modify phase, instantaneous phase, and you can modify instantaneous frequency, right? In both these cases you are modifying the argument of the cosine wave, right? You have a carrier is nothing but a cosine wave, cosine omega ct plus phi, right? So far you are modifying the instantaneous amplitude of the carrier. Now you are modifying something in the argument of the cosine function which constitutes the carrier, right? And therefore these two kinds of modulations that we just talked about, namely phase and frequency modulation, they are also broadly known by the name of angle modulation, because you are basically one way or the other modifying the instantaneous total angle of the carrier. Okay, so we broadly call it angle modulation. So if you were to write down an expression for a general form of the angle modulation, you could say that your modulated signal x of t now is a cosine omega ct plus a phase function which is time varying. Okay, so your basic carrier frequency is still omega c, but the angle of this cosine wave or the phase of this cosine wave is a time varying function, and this function captures the information that you want to convey, right? So the modulating signal m of t somehow modifies this phi of t appropriately, right? Now it will be convenient because we will now find it in many cases convenient to work with complex representation of signals. It's really makes complex representation makes life pretty easy as far as analysis goes, right? So it's also convenient to write this as real part of a times exponential of j omega ct plus phi of t. Okay, and for this reason sometimes this modulation, these sets of modulations are also known by the name of exponential modulations. Excuse me, exponential modulation. So these are the various names: phase modulation, frequency modulation, angle modulation, exponential modulation. They all refer to this kind of stuff. All right. Now in this context, let's define this total argument of the cosine wave or of the exponential function. Let's denote it by theta sub it, right? And theta sub it will be defined as the instantaneous phase of the carrier. Is that okay? Now how is instantaneous frequency related to instantaneous phase? Can you say anything? Suppose I ask you that at any particular time this quantity is theta it, right? How can I derive the instantaneous frequency from the instantaneous phase? Okay, let me help you. Suppose phi of t was 0, it was constant. What is the instantaneous frequency? What is the instantaneous phase? Omega ct or omega ct plus phi.
Theta is the instantaneous phase of the carrier or the modulated signal?
Well, I say when I say carrier, in many cases I use the terms carrier and modulated signal interchangeably, right? The carrier, because in this case carrier is not sent by itself, carrier is sent along with its modulation, right? So we are referring to these things almost interchangeably in this case, right? Okay, so let me come back to my question. Suppose phi of t was a constant, and so your phase theta it would be omega ct plus phi. What is the instantaneous frequency now? In fact, the frequency is constant now. What is the value? Omega c. How do you obtain it from theta it? Take the instantaneous derivative, right? The derivative of the phase, this is very elementary, you know it from your school physics, right, is nothing but the derivative of the instantaneous phase. So I could define therefore a quantity omega sub it, right, which is equal to d theta I by dt, and that's defined as the instantaneous frequency. Of the carrier or of the modulated signal, if you understand what I mean, right? And what would this be equal to in this case? Suppose this is your instantaneous phase, what will this be equal to? So your in this case your theta sub it is omega ct plus phi of t. That means your instantaneous frequency is omega c plus d phi by dt. Now let me introduce some more terms. Whereas theta it refers to the phase of the carrier, we should also give a name to phi of t, right? Normally when you talk about phase, actually you refer to this, but really speaking that's the precise meaning of phase, right? So what should we call phi of t? We call it phase deviation, right? If you had a pure sinusoidal signal, the phase would have gone like omega ct, right, as a function of time. Now on top of that phase variation, you have an additional phase deviation due to phi of t. So we call it the phase deviation, right? So phi of t is also called phase deviation or instantaneous phase deviation. Likewise, d phi by dt, which appears here, right, should be called instantaneous frequency deviation. So we have the concept of instantaneous phase deviation, instantaneous frequency, and instantaneous frequency deviation. Because we shall talk in these terms, so I would like all of you to understand these terms once for all. These are definitions of these terms. All of you clear about these definitions? So now that we have worked with the basic terminology, we have defined the basic terminology, let us define what is phase modulation and what is frequency modulation, right? Now we are ready to talk about these two kinds of modulation. Okay, phase modulation, we say that a carrier is phase modulated. Any suggestions? What should be the definition of phase modulation? Suppose I allow you to define it yourself. Phi t is a phi of t, the instantaneous phase deviation, should carry the message information, right? Therefore it should be made proportional to the message signal, right? That should be the obvious way of defining a phase modulated signal. So in this case we say that phi of t is chosen to be some constant times the message signal. So the constant I am denoting by k sub p, or the phase modulation constant, or you can also call it the phase sensitivity of the modulator, right. So since this will be in radians, phase is measured in radians, and this will be typically in volts, right. So the constant k sub p would have the dimensions of radians per volt, right. So basically a phase modulator would produce a phase deviation in proportion to the message signal amplitude at time t. And in the same token, frequency modulation should be defined in terms of d phi by dt. The instantaneous frequency deviation should be made proportional to the message signal, right, and that is precisely the definition of frequency modulation. Actually, since these two modulations are so similar to each other, we usually study them together rather than separately, and wherever there is a comparison, we discuss that comparison, right. Otherwise, many properties of the phase and frequency modulated signals are very similar to each other, right. So in this case, d phi by dt is made proportional to the message signal, and I am calling the proportionality constant now as k sub f, right. So k sub f would have the units of radians per second per volt, right, or if you divide it by 2 pi, 1 by 2 pi on both sides, even then kf remains the same, okay. What will be the expression for phase in this case? If you take the integral of this will become the phase, instantaneous phase deviation, equal to k sub f integral minus infinity to t ms ds, right. So these are the two ways in which you define frequency modulation. Either you say that the instantaneous frequency deviation is proportional to mt, or the instantaneous phase deviation is proportional to the integral of mt, right. This basically follows from this, integrating both sides. Fine. These are fairly simple concepts so far. I don't think there should be any difficulty. So if I were to write an expression for the phase modulated signal x of t, it is now very clear what it should be. It should be a cosine omega ct plus k sub p times mt, because your message signal, your instantaneous phase deviation is proportional to mt, and the FM signal, the frequency modulated signal, would be a cosine omega ct plus k sub f integral from minus infinity to t ms ds. I hope again it's obvious, right. We are just substituting for phi of t. Phi of t in this case is this integral. In the case of phase modulation, it is equal to kp times mt. Any questions? It will be interesting to see what kind of waveforms come out of these definitions. What is a typical waveform for frequency modulation, and what is a typical waveform for phase modulation? So let me attempt to plot some waveforms. I am not extremely good at that, but I think we will try to. Let me try to plot all the waveforms that we have discussed so far. Let me take a sinusoidal modulating signal, right. So this is my mt, this is the time axis, this is the instantaneous amplitude, right. Now what would the amplitude modulated signal look like? I was afraid that I will not be able to do a very good job, and that is what is happening, but does not matter. I think you can still follow what I am trying to do. The instantaneous amplitude of the carrier is made proportional to the message signal. That is what the waveform was like. So, x sub AMT was like that. Amplitude was dependent on the amplitude of the modulating signal, right. Now, what do we have? Let us talk about frequency modulation first. It is slightly easier to imagine the waveform. The instantaneous frequency, let us say you have some carrier frequency when the amplitude is 0, right. Let us call it f sub c or omega sub c, right. So, when the amplitude is positive, the frequency will be larger, right. It will be more than f c or more than omega c. When the amplitude is negative, it will be less than omega c. So, as the amplitude, let us say, varies from some peak value plus a to some trough value minus a, right. The frequency will vary from fc plus some value, let us call it delta f, to fc minus delta f, and the frequency will be the largest at the peak value and will be the smallest at this point, right. Now, so now can you imagine what the waveform looks like? The amplitude of the waveform is not being changed, is not being modified. So, the amplitude remains constant. So, basically the cycles which constitute the cosine function, they are either occurring close together, they are very short, either the cycles are very short in duration or the cycles are slightly longer in duration, right. Here the cycles will be most compressed, the shortest, right, because the frequency is the highest. Here the cycles will be the least compressed, most rare, right. So, the cycles will be slightly far apart from each other, right. So, that is the way the waveform will look like. So, if I were to capture this at this point, you expect the cycles to be very closely spaced. At this point, you expect the cycles to be sparsely spaced, right. So, that is, you have to draw a waveform which looks like that. Amplitude is constant, right. This is, I am just plotting this amplitude. So, it may look like this. And at this point, they have to be rather sparsely placed. I will explain it again. I have attempted to plot this. I do not know how accurately I have been able to do that, but let me repeat what I am saying. Let me again go back to this reference waveform, the modulating signal. We are making the instantaneous frequency proportional to the message signal amplitude. The message signal amplitude is the largest here, right. Therefore, the instantaneous frequency should be the largest at this point in time, right. When you say the instantaneous frequency is large, that means the cosine wave varies rapidly at that frequency, at that time instant. That means the consecutive cycles are closely spaced. The time period is smaller. Frequency is large means the time period is smaller, right. So, the time period is smallest here. So, the waveform looks compressed at this point, right. Where the amplitude is the smallest, the instantaneous frequency would be the smallest, right, and therefore, the cycles of the cosine wave will look farther apart, will be more sparsely spaced, and therefore, that is precisely what you see, right. The time period is much larger here, the time period of the cosine wave is much larger here, right. This is a rough plot and an argument for this plot that I have presented. Yes, please.
Are we trying to make the phase frequency component proportional to the amplitude of the message signal or the magnitude of the amplitude? In the sense that
no, it has to be proportional to the actual value of the amplitude, because you want to capture the information from the instantaneous frequency, right. If you are very proportional only to the magnitude, the sign information about the message will go away, which you don't want to go away, right. Is that clear? So the definition was very clear. We wanted the instantaneous frequency deviation to be proportional to MT, not proportional to magnitude of MT. Right? Very important. So the question was whether it is proportional to MT or proportional to mod of MT. The answer it is proportional to MT and not to mod of MT. That's the case by any modulation. For example, even amplitude modulation, we wanted the instantaneous amplitude to be proportional to the message signal, particularly in the case of DSP AM, right? Because there we wanted to capture the or recover the message information by just looking at the envelope, right? So is that okay? Does this waveform intuitively appeal to you? That this is what it might look like, right? It will look like a sine wave or cosine wave, but not with regularly spaced zero crossings, right? The cycles of the cosine or sine wave would be either close by together or farther apart from each other, depending on the instantaneous amplitude of the message signal. So that if you were to try to see this waveform on the oscilloscope, this is what you will see, right? The FM waveform. Now what about the PM waveform? Anything that you can say about the PM waveform? Actually these two waveforms will look very similar to each other, because you see you are making the phase proportional to MT, but you are also therefore making the instantaneous frequency vary with respect to MT, not proportional to MT but somehow dependent on MT. Let's go back to the definition of PM, right? This is the definition of phase modulation, right? What does it mean? What can we say about the instantaneous frequency? It is proportional to the derivative of the message signal now, right? So instantaneous frequency also varies once again, but the value of the instantaneous frequency follows the behavior of the derivative of the message signal rather than the message signal directly. Is that clear? So it will depend on what is the nature of the derivative of the message signal as to what the instantaneous frequency in the phase modulation would be. So for this example, I have taken sine wave as your modulating signal. So the derivative of the message signal is a cosine wave, right? So the phase modulated signal will look like a frequency modulated signal, which is modulated by a cosine wave in this case, right? So the peak frequency there will occur at pi by 2 phase shift, right, with respect to this message signal, right? So instead of occurring here, you can say it could occur here. So the densest portion of the signal will come here, and then it will, right? So let me plot a cosine wave. Right? And the rarest will occur here somewhere. Again the densest will occur here. I do not have drawn the waveform right, but I hope you understand what is happening. Right? So this is x sub fmt, and this is x sub pmt. Are you with me? So if you have understood these waveforms, you have basically understood the nature of the FM and PM signals. Right? Any questions? Yes, please.
We are modulating the frequency over here, sir. We absolutely free from over modulation and under modulation as we had in the amplitude modulation. Because there we are getting a term which is
There is no concept of under modulation and over modulation here.
so it's free from all these things.
Yes. Right? You can make it, you can choose this constant k sub f and k sub p as you like. Right? Small or large. Right? it will imply there will be other implications of the choice of these constants, which we shall look at, but not in terms of over modulation or under modulation. Right? There will be some implications. Okay, having understood the nature of the waveforms of these two kinds of modulations that we are now studying, it is obviously now interesting to look at their spectral properties. That is the first thing we like to understand, right? What are the spectral properties of these waveforms? So now what can we say about that? Some difficulty arises, because unlike, so let me just say the topic of interest now is we would like to understand the spectrum, because it is through the spectrum that we will understand what is the bandwidth requirement. That is the first thing that we like to understand as a communication engineer, right? Bandwidth requirement if I go for FM, if I go for phase modulation, right? To do that I must understand what is the nature of the spectrum, right? So let us look at these issues: spectrum, bandwidth, etc. And of course the other parameter which is of interest is the power requirements. First difficulty that we must note is that unlike the amplitude modulation, the frequency modulated and phase modulated signals in a way are non-linear modulations. Do you appreciate this? Right? That is, they don't satisfy the superposition principle, which the amplitude modulation does, right? Particularly the DSB AM, it does, right? So these are nonlinear modulations, and because these are nonlinear modulations, the exact spectrum calculation becomes very difficult, right? Because the message signal is dependent on the modulating signal through the argument of the cosine wave, right, which is a highly nonlinear function, cosine of some mt or cosine of integral of mt, right. These are highly nonlinear functions, right. So the spectrum analysis now becomes very difficult. So exact spectrum calculation, at least for the general case where the modulating signal mt is something arbitrary, right. At least for general message signals. This was not the case, if you remember, for the case of amplitude modulation, right. I could easily express, because what happened there, all that was happening was frequency translation, which is of course one of the main objectives of modulation. It has to carry out frequency translation, right. So by choosing a carrier of some frequency f sub c, we are carrying out frequency translation even here, but whereas in the case of amplitude modulations of all kinds, you are essentially carrying out frequency translation. This is something more than that, right, because we are modifying the spectrum of the modulated signal in a rather complicated manner, right, and that complicated manner is not possible to understand when the message signal mt is some arbitrary message signal, right. However, it is possible to do these calculations for a very simple case, and we will study that case only at the moment, and that is when you choose the message signal just for the sake of this study to be a pure sinusoidal signal, right. So possible to do this calculation, possible to study the spectrum when mt is equal to, let us say, am cosine omega mt. Right? So this is a very simplistic form of the message signal, but by understanding this we understand a lot about what happens to the spectrum of the FM signal, right. So we will first try to therefore study the behavior of the spectrum of the FM signal or the PM signal when the modulating signal has a simple form, right. We know that in general the modulating signal will not be of this kind, right. It will be some waveform like speech waveform or video waveform or whatever you have, these results will not be directly applicable, but still you get a lot of intuitive understanding through this, right. So we will look at that. I will make a more general statement later. So let us start with that. So let us take mt is equal to am cosine omega mt, and the phase modulated signal, the expression for that would now become basically your instantaneous phase will be given by k sub p times am cosine omega mt, and for fm this will become, what will be the value of the instantaneous phase in the case of fm? It will be the integral of this waveform, right. So k sub f, because the constant there is k sub f, times what is the integral of this? A sub m divided by omega m into sine omega mt. So the instantaneous phase of the phase modulated signal would be like this. For the frequency modulated signal it will be like this, and let us consider fm first. So waveform x of t would be, so let me write x sub fm t. When I do not write this, I think the context will make it clear whether I am talking about fm or pm. So it will be a cosine omega ct plus, let us call it a constant beta times sine omega mt, right, where beta is defined as kf, this constant kf am upon omega m. For the case of pm this will become a cosine omega ct plus, let us call it again beta cosine omega mt, and the value of beta there would be kpm. So for pm beta would be kpam, and of course instead of sine omega mt it will be cosine omega mt, which hardly makes any difference, right. We will see that. So let us try to study this signal. Now how can I study the spectral properties of this signal? Can you suggest? Is there a suggestion from the floor as to how we can study the spectral properties of this signal? Is there something about this signal that strikes you? Can you speak a little loud so that everybody can? Phasor representation. Phasor representation does not help us in studying the spectrum very much. It helps us to study the behavior of the instantaneous envelope or instantaneous phase, but not the spectrum. Spectrum, if you remember, you have to go somehow in the frequency domain. To study the spectrum you have to go into the frequency domain. What is the most convenient frequency domain representation that I should go for here? Well, you could say Fourier transform, but Fourier series would be more apt. Why? Because you can see it is a periodic signal, and that was the reason why I chose the modulating signal to be a cosine wave, right. Okay, if it is not clear, let me look at the complex representation. You can think of x of t as the real part of a times the real part of e to the power j omega ct into e to the power j beta sine omega mt. Is that okay? It is the real part of e to the power j omega ct plus beta sine omega mt. I have separated that out and I write like this. Okay. Can you see that this is a periodic signal? E to the power j beta sine omega mt, right? Sine omega mt is a periodic function, so e to the power j beta sine omega mt is a periodic function with the same period, right? So since this is a periodic function, it's a complex periodic function, of course. I can represent it by a Fourier series, and therefore I can study the spectrum by looking at the Fourier series of this function. Okay. So let's do the Fourier series expansion of e to the power j beta sine omega mt. Okay. What is the Fourier series expansion? We write x of t equal to and going from minus infinity to infinity I should use some other waveform. I am looking at this function. This function I am calling it f of t. Some coefficient c sub n into e to the power j n omega mt, that is it, right. So the coefficients of Fourier series are c sub n's. This is the nth harmonic. The period, the frequency, the fundamental is at omega m, right. So we need to find what is c sub n. Integral from over the period, and what is the period here? Minus pi by omega m to pi by omega m. The period is, total period length is 2 pi by omega m, which I am dividing between minus pi by omega m to pi by omega m into the function f t, which is e to the power j beta sine omega mt into e to the power minus j n omega sub m t dt divided by the period. And how much is the period? So it will become omega m by 2 pi. Reciprocal of the period. Period is 2 pi by omega m, so you are dividing it by the period, which is omega m by 2 pi. Okay. To simplify, to see what this looks like, let me put omega mt equal to some variable u, right. So this will become 1 by 2 pi minus pi to plus pi e to the power j beta sine x minus nx dx. I am sorry, it should be u. All right, let me make this x. Right, I am putting omega mt equal to x, and then it becomes this. Right? Anyone familiar with this function? You have done it in your maths course. You remember what this is? This function, this integral? Not familiar? Not at all familiar? Not beta function. It is a Bessel function. You have not done Bessel functions? If you say so, I don't know. That's usually not the case at this time. Everybody is familiar with Bessel functions. All right, doesn't matter. Let's define this. This is the definition of the Bessel function, which is denoted by j sub n. Bessel function of order n is denoted by j sub n, right? And x is here a dummy variable. What is the constant here? What is the parameter in the integral? Which will definitely be this result will be a function of beta, right? N of course comes here. The dependence on n is already there. C sub n is equal to this, right? So it is equal to there is a dependence on n displayed here and the dependence on n displayed here, right? The only other parameter left is beta. So this is called Bessel function of order n with argument equal to beta. Okay. So these are very very well studied set of functions, and its properties are highly documented, readily available in books of mathematics. But unfortunately, this function cannot be expressed in a closed form. It is expressed only in terms of this integral. Right? In spite of that, its properties are very well studied. Its values are documented in the form of table of Bessel function values. So for different values of beta, you have tables available for J0 beta, J1 beta, J2 beta, etc. for all values of beta. Right? So these are available in the form of tables in standard text. Right? Similarly for J minus 1 beta, J minus 2 beta, etc. and for all values of beta. So therefore, what we find is that the nth coefficient of the Fourier series of e to the power j beta sine omega mt is nothing but g and beta. Right? So can we come back to our original purpose? Our original purpose was to study the signal. Right? So instead, I have first looked at this signal, from which I can reconstruct x of t. Right? This I am writing in terms of its Fourier series. So let me substitute this in terms of its Fourier series. This will be what kind of Fourier series is this? Complex Fourier series. So your x of t is a times real part of e to the power j omega ct, and what is the complex Fourier series that we have just derived? C sub n e to the power j n omega mt, right? And C sub n is nothing but j n beta, right? So this becomes a times real part of, now let me combine this, I can write like this, n going from minus infinity to infinity, j n beta, and if I combine these two terms, what will I get? E to the power j omega c plus n omega m t, right? I have taken the term e to the power j omega ct inside this summation, so it will multiply every term, right? And that's what you will get. The nth term will be omega c plus n omega mt. And now, if I take the real part, this becomes that's what you get. So a FM signal, I have obtained a series expansion for the FM signal. But it is not precisely a Fourier series expansion of the FM signal. Can you appreciate that? Because the terms here are not harmonics of omega c plus omega m, right? The terms here are omega c plus minus n omega m. The harmonics were coming because of this component here, right? So in any case, it's a frequency domain representation. I have expressed x of t in terms of cosine waves of different frequencies, right? So in that sense, it captures the spirit of spectrum representations, any frequency domain representation. I have expressed x of t. After all, what is Fourier series? You are expressing a given signal, a given periodic signal in terms of more basic signals, which are the sinusoids of different periods. Right? Same thing is true here. X of t is comprised of frequency components which are present in this series expansion. Right? So let me just complete this. So let me complete the statement. X of t, therefore, we can say is comprised of frequency components omega c and omega c plus minus n omega m, and going from minus 0 to infinity, or if you are saying omega c plus n omega m from minus infinity to plus infinity. Yes, please. What is the question?
So G and beta is
G and beta is a real value. No, it turns out to be a real value. Okay. We'll study the properties of G and beta. I will not really study the properties of G and beta, but I'll summarize the properties of the Bessel functions for you if you have not done anything, right? You have not done that. Doesn't matter. The important properties which are relevant to our study will enumerate. Okay, we will not go into the study of the Bessel functions, but some of the things that we should know about them, we will summarize that. Okay. So this tells us a few things about the FM signal. What are the things it tells? First of all, our modulating signal was a signal of frequency omega m. Let's keep the AM signal as our reference point for the study. When the modulating signal is sinusoid of frequency omega m, what were the frequency components in the AM signal? There was a carrier component if you didn't suppress the carrier, omega c, and there were the components omega c plus omega m and omega c minus omega m. What do we find here? We not only have the components omega c plus omega m and omega c minus omega m, but omega c plus 2 omega m and omega c minus 2 omega m, and so on and so forth ad infinitum, right? We have still two side bands, one set of frequency components lying above omega c, the other set of frequency components lying below omega c, but each of these two side bands occupies a very large spectral domain, right? Theoretically going up to infinity. And this is the case when the input signal contains only a single frequency component, right? So that's the spectrum of an FM signal is very, very different from that of an AM signal. That's the first thing to learn, right? The next thing, the additional thing that we like to learn is, okay, theoretically it appears that the bandwidth of this signal is infinity, right? That's what it appears. But practically it turns out that this function J and beta, as you increase the value of n, its magnitude decreases, right? So not all the components are significant, right? A certain number of frequency components are significant, which will depend on the value of beta, right? And how many components are significant will therefore decide what is the effective bandwidth of the FM signal. Theoretical bandwidth is infinity, but practical bandwidth will be more reasonable. It will be some practical value which will depend on the value of beta. So bandwidth will now depend on beta, which is, incidentally, I have not defined what is beta. I have defined beta in terms of the constants, but it is also called the modulation index, right, in this case. So the spectral properties of the signal will therefore depend on the modulation index beta, right? So we will look at these things in more detail next time.